The universe hums with secrets, whispers in the dark that we're only just beginning to hear. Picture this, a signal, sharp and sudden, slicing through the cosmic silence from a galaxy billions of light years away. It arrives without warning, without explanation, and then it's gone. These are the unexplained galactic signals, the universe's cryptic messages, and they've left astronomers scrambling for answers. What could possibly produce such bursts of energy? Are they the echoes of collapsing stars, the signatures of advanced civilizations, or something even more extraordinary? One thing's certain, these signals defy everything we thought we knew about the cosmos, and they're rewriting the rules of astrophysics as we speak. For decades, scientists have trained their telescopes on the sky, hoping to catch these fleeting cosmic enigmas in the act. Some last mere milliseconds, others repeat in patterns that tease us with the possibility of meaning. Each one is a puzzle wrapped in the vastness of space, and every new discovery deepens the mystery. Imagine, these signals travel across unimaginable distances through time itself to reach us. They're like postcards from the edge of reality, stamped with questions we can't yet answer. And the most thrilling part, we've only scratched the surface. For every signal we've detected, there are countless others still waiting to be found, each one holding the potential to upend our understanding of the universe. Today, we're diving into 30 of the most baffling galactic signals ever recorded, along with the theories that scientists believe might explain them. From bizarre natural phenomena to whispers of extraterrestrial technology, we'll explore the cutting-edge ideas that could finally crack these cosmic codes. This isn't just a journey through space, it's a detective story, a chase after some of the greatest unknowns science has ever faced. So buckle up. By the end of this, you'll see the night sky not as a static canvas of stars, but as a dynamic, whispering frontier, alive with mysteries begging to be solved. The universe is talking. Are you ready to listen? The night of August 15, 1977, started like any other at Ohio State University's Big Ear radio telescope. Then at 10:16 p.m., the unthinkable happened. A signal burst onto the printout so intense, so unnatural, that astronomer Jerry Amon circled it in red ink and scribbled a single word next to it: wow. That scribble would give the signal its name, but the mystery behind it would haunt science for decades. This wasn't just any blip. The wow signal roared in at 1420 megahertz, the exact frequency scientists had theorized an extraterrestrial civilization might use to broadcast. It lasted 72 seconds, the full window the telescope could observe it before vanishing without a trace. And here's the kicker, it's never been detected again despite dozens of attempts. The signal came from the direction of the constellation Sagittarius, but scans of that region have turned up nothing, no star, no galaxy, no known cosmic phenomenon that could explain it. So what was it? Some scientists argue it could have been a freak burst from a comet's hydrogen cloud. Except comets don't emit such focused, powerful signals. Others suggest it might have been a military satellite test, but declassified records show no such activity at that time. Then, of course, there's the tantalizing possibility: what if it was deliberate? A fleeting hello from a civilization far beyond our own. The signal's narrow frequency range and sudden disappearance fit the profile of an intentional transmission rather than random cosmic noise. Yet the wow signal refuses to give up its secrets. No repeat detections, no natural explanations that fully fit. It stands alone, a one-time cosmic shout into the void. And that's why, nearly 50 years later, it remains the gold standard of unexplained signals. Not just for what it was, but for what it represents, proof that the universe might still be hiding voices we've only begun to hear. While the wow signal remains a one-time cosmic anomaly, another mysterious signal has proven far more chatty. Enter FRB 121102, the first fast radio burst ever observed repeating its performance. Discovered in 2012 by the Arecibo Observatory in Puerto Rico, this signal didn't just flash and vanish like its counterparts. It erupted again and again, each burst a fleeting blast of radio waves from a dwarf galaxy 3 billion light-years away. What sets FRB 121102 apart isn't just its persistence, it's the bizarre structure of its emissions. Most fast radio bursts are chaotic, but this one follows a rhythm. Some bursts arrive in clusters with milliseconds between them, while others space themselves out over days or weeks. It's almost as if whatever's producing them operates on a schedule we can't quite decode. So what's behind this cosmic Morse code? One leading theory points to magnetars, neutron stars with magnetic fields so intense they could strip the electrons from atoms halfway across the galaxy. When these stellar corpses experience starquakes, cracks in their crusts might unleash titanic energy surges, potentially explaining the bursts. But here's the catch: no known magnetar emits signals with such precise repetition. Then there's the more speculative idea: cosmic strings, hypothetical fissures in space-time left over from the Big Bang. If these strings vibrate or snap, they could theoretically release energy matching FRB patterns. It's a fringe theory, but the universe has surprised us before. And yes, the extraterrestrial angle persists. Some researchers argue the burst structure resembles what we'd expect from massive alien energy projects, perhaps propulsion beams or communication attempts. But without definitive proof, it remains science fiction's favorite explanation. What makes FRB 121102 so compelling is its defiance. It's not just a mystery, it's a conversation. Unlike one-off bursts, this signal keeps talking back, daring us to understand it. Whether it's a dying star's death throes or something far stranger, one thing's clear: the universe loves a good encore. Before fast radio bursts had a name, before scientists even knew to look for them, the universe sent us a wake-up call. In 2007, astrophysicist Duncan Lorimer and his student David Narkevic were sifting through old data from Australia's Parkes radio telescope when they stumbled upon something extraordinary. Buried in observations from 1998 was a radio pulse so powerful, so fleeting, it defied all known astrophysical explanations. Lasting just 5 milliseconds, this burst, now called the Lorimer burst, packed more energy than the sun emits in 30 days. And it came from somewhere beyond our galaxy, a staggering 3 billion light-years away. What could possibly generate such an intense, short-lived signal? The leading theory points to catastrophic cosmic collisions, specifically two neutron stars spiraling into each other in a violent merger. When these ultra-dense stellar remnants collide, they might unleash titanic magnetic shocks capable of projecting focused radio waves across the universe. But there's a problem. Neutron star mergers are rare events, and subsequent searches found no afterglow or gravitational waves to corroborate this explanation for the Lorimer burst. Then there's the black hole angle. Supermassive black holes lurking at the centers of galaxies occasionally shred passing stars in what astronomers call tidal disruption events. The resulting plasma jets could theoretically produce bursts like this, except the Lorimer burst's clean, single pulse doesn't match the messy, prolonged emissions these events usually create. More exotic explanations have emerged. Some theorists suggest collapsing blitzars, a hypothetical type of neutron star that avoids becoming a black hole by shedding its outer layers in a final, energetic outburst. Others propose cosmic strings, not the sci-fi kind, but theoretical defects in spacetime itself, snapping like rubber bands and releasing pent-up energy. What makes the Lorimer burst so pivotal isn't just its mystery, but its legacy. It was the first domino in a chain reaction of discovery, proving that the cosmos occasionally screams where we expected only silence. Every fast radio burst detected since traces its scientific lineage back to this 5-millisecond enigma, a reminder that sometimes the most universe-shattering revelations arrive quietly, hidden in data, waiting decades for someone to listen. Deep in the static of space, where cosmic whispers fade into background noise, one signal managed to spark a debate that still simmers today. It's called SETI-02+14a, a cryptic string of letters and numbers that belies its extraordinary claim to fame. Detected back in 2003 by the SETI at Home project, this faint radio pulse appeared to be coming from a patch of sky near the Pisces constellation, roughly 1,000 light-years away. But what made scientists do a double-take wasn't just its location, it was the frequency. SETI-02+14a was transmitting at 1,420 MHz, the same sweet spot as the infamous WOW signal, right where scientists predicted an advanced civilization might broadcast. Now, here's where things get contentious. The signal wasn't constant, it drifted. And not randomly, it drifted in a way that mirrored how a signal from a planet orbiting a distant star would shift due to the Doppler effect as it moved toward and away from Earth. That kind of precision doesn't just happen in nature, at least not often. Proponents of the artificial origin theory latched onto this detail, arguing that only a technological source, like a transmitter on an exoplanet, could produce such a telltale pattern. The implication: we might have just eavesdropped on an alien radio beacon, but skepticism quickly poured in like cosmic rain. For starters, the signal was weak. Extremely weak. So faint that some researchers argued it could have been nothing more than terrestrial interference, a passing satellite, a glitch in the software, or even a microwave oven in the observatory cafeteria. Yes, that's happened before. Then there's the repetition problem, or lack thereof. Despite multiple follow-up observations, SETI-02+14a never showed up again. In science, one-time detections are treated like mirages until proven otherwise. And yet it lingers in the archives of cosmic mysteries, because even if the signal was a fluke, its properties push the boundaries of what we consider plausible natural phenomena. No known pulsar, no quasar, no collapsing star behaves quite like this. The universe has a way of surprising us, of dangling possibilities just out of reach. Whether SETI-02+14a was a cosmic prank, a technical hiccup, or the real deal, it serves as a humbling reminder: we're still learning how to listen in a universe that has only begun to speak. In the quiet expanse of our cosmic backyard, just 4.2 light-years away, something peculiar woke up astronomers in late 2020. It came from Proxima Centauri, the closest star to our Sun and home to at least one known exoplanet, dubbed BLC-1. This signal wasn't just another blip in the data. It was narrowband, meaning it occupied a sliver of the radio spectrum where natural cosmic noise rarely treads. The frequency, a crisp 982 MHz, conveniently free from human-made interference, yet suspiciously close to the range we'd expect from a deliberate transmission. What made BLC-1 so electrifying was its behavior. Unlike the erratic scatter of natural radio emissions, this signal drifted in frequency over time, mirroring the motion you'd expect if it originated from a planet orbiting Proxima Centauri. And here's the kicker: it appeared only when the telescope was pointed at the star, vanishing when aimed elsewhere. For a fleeting moment, it seemed like the Breakthrough Listen project, a decade-long search for extraterrestrial intelligence, had hit the jackpot. But science thrives on skepticism. As excitement spread, so did scrutiny. Some researchers argued the signal could have been a rare burst from one of Proxima Centauri's notorious stellar flares, a red dwarf known for its violent outbursts. Others pointed to human technology, a passing satellite perhaps, or even interference from a malfunctioning device on Earth, the most damning evidence. Follow-up observations failed to detect BLC-1 again, leaving its origin hanging in the void between possibility and disappointment. Yet the debate isn't settled. The signal's properties don't neatly fit any known natural explanation, and its frequency drift remains oddly precise for random noise. Could it have been a glitch? Absolutely. But glitches don't usually align so perfectly with our expectations of an alien broadcast. Whether BLC-1 was a cosmic hello, a stellar tantrum, or just faulty electronics, it underscores a thrilling truth. Even the closest stars still hold secrets we're only beginning to decode. The search continues because in a universe this vast, the next signal might not just whisper, it might answer. Most cosmic signals play by the rules of chaos, unpredictable, fleeting, impossible to pin down. But FRB 180916 laughs in the face of randomness. Discovered by the CHIME telescope in 2018, this fast radio burst isn't just repeating, it's keeping time. Every 16.35 days, like clockwork, it erupts in a 4-day frenzy of radio bursts before going silent for 12 days. It's the closest thing we've seen to a cosmic metronome, and it's rewriting what we thought we knew about these enigmatic signals. So what could possibly explain this celestial rhythm? One leading theory points to a neutron star locked in a slow, gravitational dance with a massive companion, perhaps a black hole or another neutron star. As the pair orbits, the intense tidal forces might periodically twist the star's magnetic field, triggering bursts when the alignment is just right. Think of it like a lighthouse beam sweeping past Earth, but instead of light, it's blasting radio waves across the universe. The 12-day quiet period, that's when the companion's shadow blocks the bursts from our view. Then there's the precessing magneta model, a neutron star wobbling like a spinning top. As its magnetic axis tilts over weeks, it might briefly align with Earth, allowing us to catch its outbursts before it wobbles away again. It's an elegant explanation, except for one hiccup. No known magneta wobbles on a 16-day cycle. Nature rarely follows human-made calendars this precisely. And of course, there's the elephant in the cosmos. Could this be artificial? Some theorists speculate about alien megastructures, hypothetical power beams, or communication arrays sweeping past us as their source rotates. The timing does fit what we'd expect from a deliberate, repeating broadcast. But before you picture interstellar radio towers, remember, extraordinary claims demand extraordinary evidence. What makes FRB 180916 so mesmerizing isn't just its regularity. It's the defiance of expectations. The universe isn't supposed to be this orderly, this predictable. Whether it's a cosmic pendulum or something even stranger, this signal proves one thing. When it comes to deep space, we're still learning the steps to a dance we can't yet hear in full. Some stars flicker like candles in the wind, but KIC 8462852, better known as Tabby's star, doesn't just flicker, it plunges. Discovered in 2015 by citizen scientists combing through Kepler Space Telescope data, this distant sun, roughly 1,200 light-years away in the Cygnus constellation, behaves unlike anything else in our cosmic records. Most stars dim by fractions of a percent when planets pass in front of them. Tabby's star, it drops up to 22% of its brightness at irregular intervals, as if something colossal and utterly unpredictable is drifting across its face. The first instinct was to blame a swarm of comets. A massive family of icy debris orbiting the star could theoretically block its light in erratic patterns. But calculations quickly unraveled. To explain the observed dimming, you'd need millions of comets, an implausible number for a star of this age and type. Plus, comets leave traces of heat when they vaporize, and Tabby's star showed no such infrared signatures. Then came the dust theory. Maybe a vast, uneven cloud of cosmic particles, remnants of a shattered planet or a colliding asteroid belt, was spiraling around the star. Dust scatters light differently than solid objects, which might account for the dimming's strange wavelengths. Observations in 2018 lent some support. The star dimmed more in blue light than red, a telltale sign of dust's presence. Yet even this explanation doesn't quite fit. The dimming events are too deep, too sudden for ordinary dust clouds. And then, of course, there's the idea that ignited imaginations worldwide, the Dyson sphere hypothesis. Proposed by physicist Freeman Dyson in the 1960s, a Dyson sphere is a hypothetical megastructure, a vast array of solar panels or habitats built by an advanced civilization to harness a star's energy. Could the irregular shadows crossing Tabby's star be the silhouettes of such a construct? It's a tantalizing thought, but skepticism runs deep. Nature rarely needs aliens to explain its oddities, and no direct evidence, like artificial radio signals, has ever been detected from the star's direction. Yet Tabby's star keeps defying easy answers. Recent studies suggest a mix of phenomena might be at play: fine dust, coarse debris, and maybe even stellar magnetism warping our view. Each new observation peels back another layer of mystery, proving that sometimes the universe's most fascinating puzzles aren't just about what we find, but what refuses to be neatly explained. In 2015, astronomers monitoring the Russian Ratan 600 radio telescope caught something that sent ripples through the scientific community, a signal so unusual it sparked whispers of a breakthrough. HD 164595, a sun-like star 94 light-years away in the constellation Hercules, had apparently spoken, or at least that's how it seemed. The signal, detected at 11 GHz, was narrowband, a hallmark of artificial transmissions, and it pulsed with an intensity that couldn't easily be dismissed as cosmic static. For a brief, electrifying moment, the possibility of contact hung in the air. What made this detection so compelling was the star itself. HD 164595 isn't just any star. It's a virtual twin of our Sun, slightly older but strikingly similar in size and composition. And in 2016, astronomers confirmed it hosts at least one Neptune-sized planet, a solar system like ours with a potentially habitable zone. That's the kind of place we'd expect to find life if it's out there. The signal's frequency was another red flag. 11 GHz sits in the microwave range, a quiet part of the spectrum where natural cosmic noise is minimal, but human-made signals like radar or satellite communications thrive. Skeptics were quick to pounce. The signal was never observed again, despite repeated scans, a classic red flag for terrestrial interference. Was it a military satellite test? A glitch in the telescope's electronics? Even the discoverers admitted the most likely culprit was human-made noise reflecting off space debris or atmospheric turbulence. But here's the twist. HD 164595 resides in a patch of sky rarely surveyed by Earth satellites, making accidental interference statistically less probable. The debate took a sharper turn when researchers crunched the numbers. If the signal was artificial and intentional, the energy required to beam it across interstellar space would be staggering. A civilization capable of such a feat would need technology harnessing the equivalent of a star's entire energy output. That's Kardashev scale level 2 speculation far beyond our own capabilities. Unless, of course, they weren't broadcasting in all directions but targeting us deliberately. Yet for all the excitement, the HD 164595 signal remains in limbo, a tantalizing maybe in the search for extraterrestrial intelligence. It's a reminder that the line between discovery and disappointment can be razor-thin in astronomy. One moment, you're glimpsing what could be the first hello from another world. The next, you're left with static and questions. But that's the thrill of the hunt. Even the dead ends teach us how to listen better. And somewhere out there, amid the cosmic noise, the next signal might not fade into silence. It might just say something back. Most fast radio bursts come from the cosmic boondocks, tiny, turbulent galaxies where star formation runs wild. But FRB 190523 broke the mold. When astronomers pinpointed its origin in 2019, they found something startling. This burst didn't hail from some dwarf galaxy's chaos. It erupted from a massive, quiet galaxy, a cosmic retirement home where stellar fireworks are rare. This wasn't just a flash in the dark, it was a signal from a place where signals like this shouldn't happen. The host galaxy, a behemoth 6 billion light-years away, spins lazily with aging stars and little of the gas that fuels star births. It's the last place you'd expect to find the violent origins of an FRB. Most repeating bursts trace back to young, messy galaxies where magnetars, highly magnetic neutron stars, are born in supernova explosions, but FRB 190523 came alone, flashed once and left no calling card. So what could have sparked it in such a serene neighborhood? One theory points to an unlikely culprit, a wandering black hole. Not the supermassive kind anchoring the galaxy's center, but a rogue intermediate mass black hole drifting through the outskirts. If such an object weighing thousands of solar masses collided with a dense neutron star, the resulting shockwaves might have unleashed the burst. It's a cosmic one-night stand with catastrophic consequences. Then there's the Blitzar hypothesis. Imagine a neutron star so massive it should have collapsed into a black hole long ago, held up only by its furious spin. When it finally slows down, the star's sudden collapse could release a final, brilliant radio scream, a single burst matching FRB 190523's profile. No repeats, no encore, just a stellar swan song echoing across billions of years. But perhaps the most intriguing idea involves dark matter. Some theorists suggest certain FRBs could arise from primordial black holes, hypothetical remnants of the early universe passing through neutron stars and triggering explosions. It's a fringe idea, but in a galaxy this old and quiet, fringe might be where the answers hide. What makes FRB 190523 so compelling isn't just its defiance of expectations. It's the reminder that the universe loves outliers. For every rule we think we've decoded, there's always an exception lurking in the shadows, waiting to rewrite the script. Whether it's a black hole's chance encounter or a dying star's last stand, this burst proves one thing: the cosmos still holds cards it hasn't shown us yet. In the constellation Virgo, just 11 light-years away, a small, quiet red dwarf star named Ross 128 suddenly decided to break its silence. In May 2017, astronomers at Puerto Rico's Arecibo Observatory, yes, the same facility that detected the first repeating fast radio burst, picked up something bizarre. For 10 minutes, radio waves pulsed from Ross 128 in a pattern so unusual that researchers initially hesitated to call it natural. The signal was narrowband, centered around 4 to 5 GHz, precisely the range where human-made interference loves to hide, but also, coincidentally, a window where deliberate transmissions might stand out against cosmic noise. What made this detection so puzzling wasn't just its artificial seeming structure. Ross 128 is a flare star, prone to violent eruptions of radiation that could, theoretically, mimic radio bursts. But here's the catch: stellar flares usually scatter energy across a wide range of frequencies. This signal, it was eerily focused, like a laser beam cutting through static. Even stranger, when the team pointed the telescope back at the star in follow-up observations, the signal had vanished. No repeats, no echoes, just silence. Scientists scrambled for explanations. Could it have been a satellite ghosting through the data? Unlikely. The signal's frequency drift didn't match the trajectories of any known spacecraft. A passing aircraft, the observatory's own equipment, ruled that out. Then came the flare argument, maybe an unusually coherent stellar tantrum. But modeling showed that even the most extreme flares couldn't produce such a clean, narrowband signal. The odds were slim, bordering on astronomical. And then there's the elephant in the observatory. Ross 128 hosts at least one exoplanet. It's a super-Earth, likely tidally locked, bombarded by radiation, hardly a postcard for habitability. But if, somehow, intelligence had taken root there, could this have been a stray broadcast? The timing is provocative. The signal appeared during a period when Ross 128 was relatively calm, with no major flares detected. Was it a coincidence or something more intentional? The mystery deepens when you consider the star's motion. Ross 128 is hurtling toward us at high speed, meaning any hypothetical civilization there would have known for centuries that their star was approaching another inhabited system, ours. The signal's one-off nature could suggest a targeted experiment, a brief ping to test the waters, or, of course, it could have been a fluke, a cosmic prank played by the universe's love of chaos. Despite years of analysis, the Ross 128 signal remains unresolved. It's a Rorschach test for astronomers. Some see stellar oddities, others glimpse the faintest flicker of possibility. What's undeniable is this red dwarfs, long dismissed as backwater stars, might be hiding secrets we're only beginning to tune into. And if a quiet star like Ross 128 can suddenly shout, who knows what else we've missed in the static? Deep in the heart of our galaxy, hidden behind thick clouds of interstellar dust, lies a star cluster so unusual even its name sounds like a cosmic whisper. Glimpse C01. Discovered by the Spitzer Space Telescope's infrared eyes, this tight-knit family of ancient stars shouldn't be remarkable. But in 2014, radio telescopes caught something bizarre: sporadic bursts of energy crackling from its direction with no clear explanation. What makes Glimpse C01's signal so puzzling is its location. This isn't some isolated corner of space, it's buried in the galactic center, a turbulent region where gravity twists reality and magnetic fields run wild. Normally, radio emissions from such areas come from known sources, pulsars spinning like lighthouses or supernova remnants scattering shockwaves, but Glimpse C01's bursts don't match any of these. They arrive unpredictably, sometimes vanishing for years before flaring back to life, as if the cluster itself is flickering in and out of focus. One leading theory suggests an unseen population of millisecond pulsars, neutron stars spinning hundreds of times per second, could be the culprits. Packed tightly in the cluster's core, their beams might crisscross in chaotic ways, creating interference patterns we perceive as erratic bursts. But there's a catch: no known pulsar behaves this sporadically. Their rotations are famously precise, their emissions steady as cosmic metronomes. Then there's the dark matter angle. Some researchers speculate that if certain theoretical particles, like actions, exist, they could cluster around old stars, occasionally converting into radio waves when exposed to strong magnetic fields. It's a long shot, but Glimpse C01's age and density make it a perfect laboratory for such exotic physics. But perhaps the most wild-card explanation involves colliding white dwarfs. In a cluster this dense, stars brush past each other constantly, and sometimes two dead stars might graze or merge. The resulting energy release could trigger temporary radio outbursts unlike anything we've catalogued. What's fascinating isn't just the mystery, it's the irony. Glimpse C01 sits in one of the most observed parts of the sky, yet it's as enigmatic as signals from billions of light-years away. Sometimes the universe hides its greatest puzzles not in the void but right under our noses, or in this case, buried in the glittering chaos of our own galactic backyard. For decades, fast radio bursts were cosmic puzzles with no clear solutions, flashes of energy from distant galaxies arriving without explanation. Then, in April 2020, everything changed. Astronomers caught a break in the form of FRB 200428, a burst so close and so bright, it could have been mistaken for a local radio station if not for its staggering power. What made this signal groundbreaking wasn't just its intensity, it was its origin. For the first time, an FRB was definitively traced to a known object, a magnetar named SGR 1935+25 lurking right in our own Milky Way. This wasn't just a lucky observation, it was a revelation. Magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, had long been suspects in the FRB mystery. But until FRB 200428, no one had caught one in the act. The evidence was undeniable. As the magnetar experienced a violent starquake, a sudden crack in its crust, it unleashed a burst of X-rays and gamma rays. Seconds later, a matching FRB followed, as if the star's magnetic field had twisted itself into a cosmic lightning rod, channeling energy into a focused radio blast detectable across the galaxy. The implications were staggering. Finally, here was proof that at least some FRBs could be naturally tied to the extreme physics of these ultra-magnetic stellar corpses. But just as one mystery seemed solved, others deepened. Why did this burst come with X-rays while distant FRBs don't? Why was its radio emission thousands of times weaker than its extragalactic cousins? And most puzzling of all, why haven't other magnetars in our galaxy produced similar bursts? Some scientists argue that SGR 1935 plus 25 might be a rare hybrid, a magnetar with just the right combination of spin and magnetic field strength to produce FRBs. Others speculate that distant FRBs could be magnetars on steroids, their bursts amplified by dense interstellar environments we don't see in our quieter galactic neighborhood. Yet FRB 200428's legacy isn't just about answers, it's about perspective. It showed us that magnetars can produce FRBs, but it also hinted that the universe might have multiple ways to generate these signals. Some bursts could be magnetars, others might still be collisions, collapses, or even, dare we say it, something beyond our current physics. What's certain is this: for a brief moment, the cosmos gave us a front-row seat to one of its most electrifying shows. And in doing so, it reminded us that even when we think we've cracked the code, the universe always keeps a few wild cards up its sleeve. The Andromeda Galaxy has always been a cosmic neighbor we thought we knew, a swirling giant of stars, dust, and familiar physics. Then, in 2015, something disrupted that comfort. A team analyzing archival data from the Robert C. Byrd Green Bank telescope stumbled upon a radio signal unlike anything typically seen from Andromeda's serene spiral arms. Designated as the Andromeda signal, this burst pulsed at 1.4 GHz, a frequency suspiciously close to the range used by Earth's aviation navigation systems. At first glance, it fit the profile of a human-made transmission. But here's the catch: the signal appeared to originate inside Andromeda, 2.5 million light-years away. Initial excitement flared. Could this be evidence of technology beyond our galaxy? The idea wasn't entirely far-fetched. 1.4 GHz sits in the so-called water hole, a quiet band of the radio spectrum bookended by hydrogen and hydroxyl emissions, a theoretical sweet spot for interstellar communication. But skepticism followed just as swiftly. For starters, the signal's frequency drifted in a way inconsistent with a distant origin. Instead of the smooth Doppler shift expected from a source moving with Andromeda's rotation, it wobbled erratically like a radio station tuning in and out. Astronomers soon pinpointed a more mundane culprit: a passing satellite. Earth's orbit is littered with hardware reflecting rogue radio waves, and this signal's drift matched the trajectory of a known spacecraft. Case closed? Not quite. Even after accounting for satellite interference, lingering anomalies remained. The signal's intensity was too high for a mere reflection, and its duration, several hours, defied typical satellite behavior. Some researchers speculated it might have been a rare periton, a class of radio burst once thought extraterrestrial until traced to microwave ovens at observatories. Yet no earthly appliance could explain this signal's power or apparent direction. The truth might lie in an overlooked cosmic middle ground: Andromeda's halo, a vast cloud of hot gas enveloping the galaxy, could amplify and distort distant signals, creating phantom emissions that mimic artificial broadcast. Alternatively, the signal might have been a freak scattering event, where radio waves from a pulsar or quasar bent around an interstellar dust cloud, arriving at Earth in a misleading form. What makes the Andromeda signal so enduringly fascinating isn't just its unresolved nature, but the questions it forces us to confront. Even in our own cosmic backyard, the line between natural and artificial blurs. The universe is full of echoes, mirages, and reflections sometimes. The most tantalizing signals aren't messages from beyond, but the cosmos playing tricks with the tools we use to listen. And that, in itself, is a revelation worth tuning into. The year 2020 was supposed to bring clarity to one of astronomy's most tantalizing mysteries, the strange signal from HD 164595. Instead, it reignited the debate with fresh intensity. That March, Russia's Ratan 600 radio telescope detected another unusual burst from the same star that had raised eyebrows 5 years earlier. This time, the signal clocked in at 11 gigahertz again, but with a twist. It wasn't just narrowband, it exhibited subtle frequency modulation, almost as if it carried encoded information. Scientists immediately split into camps. On one side, skeptics pointed to Earth's growing swarm of satellites. 11 gigahertz is prime real estate for military and telecommunications signals, and the modulation could have been interference bouncing off space debris. But here's where it gets complicated. Ratan 600's unique design uses a stationary reflector with movable receivers, making it less susceptible to terrestrial noise than conventional dishes. The signal also matched HD 164595's position with uncanny precision, too precise for a random glitch. Then came the timing. This detection coincided with renewed scrutiny of the star's planetary system. Advanced modeling now suggests its Neptune-sized world might share its orbit with smaller, rocky planets, possibly in the habitable zone. Could the signal have been a radar sweep from a civilization mapping nearby space? The hypothesis isn't as far-fetched as it sounds. Human radar systems like NASA's Goldstone Solar System radar sometimes leak detectable emissions into space. An advanced society might use similar technology for asteroid detection or interstellar navigation. But nature has its own bag of tricks. Some astronomers proposed an exotic stellar phenomenon, a type of plasma instability around HD 164595's magnetic poles, creating natural but narrowly focused radio spikes. Others pointed to gravitational lensing, where a foreground object briefly magnifies background radio emissions, mimicking an artificial signal, most damning. Despite extensive follow-ups by Breakthrough Listen and other projects, the signal hasn't reappeared. Yet HD 164595 refuses to be dismissed. Its solar twin status, potentially habitable planets, and now two unusual signals make it a glittering enigma in SETI catalog. Whether it's cosmic static or a hello from the Hercules constellation, this star holds a mirror to our deepest question. In a universe this vast, how do we distinguish nature's noise from someone else's signal? The answer might still be out there, waiting for the next time we point our telescopes skyward. Most fast radio bursts scream into the void with chaotic, unpolarized radio waves, but FRB 110523 didn't follow the script. Detected in November 2015 by the Green Bank telescope, this burst stood out for something bizarre. Its radio waves were twisted, not just slightly but dramatically, a property called Faraday rotation that hinted at an epic journey through some of the most extreme environments in the universe. The twist comes from magnetism. When radio waves pass through powerful magnetic fields like those around neutron stars or black holes, their polarization can rotate like a corkscrew turning as it moves. FRB 110523's waves had rotated so much, astronomers realized they must have traversed an incredibly dense magnetized plasma cloud before reaching us. The numbers were staggering. Calculations suggested a magnetic field strength of at least 10 microgauss, spread across tens of thousands of light years. That's not just a magnetic field, that's a cosmic electromagnet on steroids. So what could create such extreme conditions? One theory points to the outskirts of a galactic nucleus, where supermassive black holes churn space into a maelstrom of magnetic chaos. If the burst originated near such a monster, its radio waves could have been twisted by the black holes surrounding Plasma Taurus, a swirling donut of ionized gas threaded with magnetic fields. The only catch, FRB 110523's host galaxy hasn't been pinpointed, leaving this idea tantalizing but unproven. Then there's the cosmic filament hypothesis. Between galaxies, vast strands of ionized gas, part of the cosmic web, might harbor stronger magnetic fields than we've assumed. If the burst's path happened to graze one of these invisible threads, it could explain the extreme Faraday rotation without requiring a nearby black hole. It's a long shot, but if true, it would mean FRBs could act like cosmic probes, revealing hidden structures in the universe's scaffolding. But perhaps the most intriguing possibility involves magnetized stellar winds. Imagine a massive star collapsing into a neutron star, its outer layers ejected in a turbulent, magnetized outflow. Years later, when that neutron star emits an FRB, the signal plows through this ancient stellar wind, a relic magnetic jungle that twists the radio waves into their bizarre corkscrew shape. Supporting this, FRB 110523 showed evidence of scattering, as if its waves had been roughed up by dense plasma on their way here. What makes this burst so special isn't just the puzzle it presents, but the tool it offers. By studying how its polarization changed, astronomers could essentially map the invisible magnetic landscapes it traversed, like deducing the shape of a maze by how a ball rolls through it. Whether it's a black hole's grasp, a cosmic thread, or a dying star's ghostly wind, FRB 110523 proves these signals aren't just messages from the void. They're passports stamped by every strange frontier they've crossed, revealing a universe far more textured and magnetic than we ever imagined. The Tau Boötis system should have been just another quiet corner of the cosmos, a yellow-orange star 51 light-years away with a gas giant planet locked in a scorchingly close orbit. But in the late 1990s, something peculiar caught astronomers' attention. Radio telescopes detected strange, pulsing emissions from the star itself, not the smooth hum of stellar activity, but sharp, almost rhythmic bursts at 1420 MHz. That number should ring a bell. It's the same frequency as the WOW signal, nestled right in the range where cosmic noise gives way to potential intentional broadcasts. At first glance, the culprit seemed obvious. Tau Boötis b, the hot Jupiter whipping around its star every 3.3 days. Massive exoplanets with strong magnetic fields can generate intense auroras, much like Earth's northern lights, but powered by the star's radiation rather than solar wind. These auroras emit radio waves, a phenomenon we've detected from Jupiter itself. But here's where things get weird. Tau Boötis b's radio bursts were 10,000 times more powerful than anything our solar system's gas giants produce. Either this planet had magnetic fields rivaling a small star, or something else was amplifying the signal. One radical theory suggests the planet might be locked in a magnetic tug-of-war with its host star. Tau Boötis is unusually active, with a roiling magnetic field that could interact directly with the planet's own magnetosphere, creating a circuit of charged particles between them. Picture this: as the planet orbits, its magnetic field lines stretch and snap like cosmic rubber bands, launching bursts of energy detectable across light years. It's a tantalizing explanation, except no known physics predicts emissions this strong from such an interaction. Then there's the elephant in the observatory, the signal's unnerving coherence. Natural cosmic radio emissions tend to be messy, scattered across frequencies like static on an old television. Tau Boötis bursts, however, were narrowly focused, almost laser-like in their precision. Some researchers proposed they might be caused by a moon orbiting Tau Boötis b, a moon with a subsurface ocean like Europa, where conductive saltwater sloshing against a metallic core could generate extreme magnetic activity. But no such moon has been detected, and the energy required would dwarf anything in our solar system. Of course, the possibility that first set pulses racing among SETI scientists hasn't vanished entirely. Could the signal be artificial, a planetary radar system, perhaps, or even leakage from a civilization's power grid? The 1420 MHz frequency is suspiciously convenient, sitting in a quiet band where messages might stand out against cosmic noise. But skeptics counter that Tau Boötis B's 700 degrees Celsius temperatures make life, at least as we know it, an implausible fantasy, unless, of course, we're not dealing with surface dwellers, but with something far beyond our frame of reference. What makes Tau Boötis so endlessly fascinating isn't just the unanswered questions. It's the precedent it sets. If a relatively nearby star system can produce radio bursts this baffling, then the universe might be teeming with phenomena we've barely begun to catalog. Whether it's a magnetically supercharged planet, a hidden moon's cry for attention, or something even more extraordinary, one thing's certain: Tau Boötis refuses to be ignored. Every flicker from its direction is a reminder that sometimes the most tantalizing cosmic whispers come not from the void's edges, but from right next door. Deep in the heart of the Milky Way, where gravity twists space-time into knots and stars crowd like commuters in a cosmic subway, something peculiar flickered to life in the early 2000s. Astronomers dubbed it GCRTJ 1745-3009, a clumsy name for one of the galaxy's most enigmatic radio transients. Unlike the usual suspects, pulsars with their metronome ticks or quasars blazing with ancient light, this source didn't play by any known rules. It flared to life over minutes, blasting out circularly polarized radio waves in 5 distinct bursts, each 10 minutes apart. Then, as suddenly as it appeared, it vanished. No afterglow, no repeats, just silence where there had been a radio shout. The strangest part, GCRTJ 1745-3009 wasn't some distant interloper. It sat just 300 light-years from Sagittarius A, the supermassive black hole anchoring our galaxy. That proximity raised eyebrows. Galactic centers are extreme environments where gravity, magnetism, and radiation conspire to warp normal physics. Could this signal be the cry of a neutron star stretched to its limits? One theory suggests an ultra-long period magnetar, a neutron star spinning so slowly it takes hours or even days to complete a rotation. Normally, such lethargic spins wouldn't produce coherent radio bursts, but near a black hole, tidal forces might twist the star's magnetic field like a rubber band, storing energy until it snaps back in explosive radio releases. Then there's the black hole tango hypothesis. Imagine a neutron star locked in a tight orbit with an intermediate mass black hole, a missing link between stellar and supermassive black holes that's eluded detection. As the star whips around, its magnetic field could get shredded by the black hole's gravity, creating temporary hotspots that flare as they align with Earth. The 5 bursts, that could be the star's rotation timing, with each pass through a plasma curtain triggering another eruption. But GCRTJ 1745-3009 has one more curveball: its circular polarization. Most cosmic radio sources emit linear waves vibrating in a single plane. Circular polarization suggests a magnetic environment so twisted, it spirals the waves like a corkscrew. Only a handful of objects like plasma jets from black holes are known to produce such signals naturally. Which begs the question, could this be a black hole's fingerprint after all? A flicker from an accretion disk's turbulent edge, or even a magnetic reconnection event, a cosmic short circuit, in the chaotic gas clouds orbiting Sagittarius A. Theories abound, but the truth remains locked in the galactic core's vault. No repeats have been detected since those 5 flares in 2003 and 2004, leaving astronomers with a frustratingly sparse data set. What's certain is this: GCRTJ 1745-3009 defies our neat astrophysical categories. It's not quite a pulsar, not quite a black hole echo, just a whisper from the universe's most anarchic neighborhood, reminding us that even in our own backyard, the cosmos still has tricks up its sleeve. Some cosmic signals arrive with an address a host galaxy scientists can point to and study. FRB 150215 wasn't one of them. When this fast radio burst flashed into existence in February 2015, astronomers swung their telescopes toward its origin, expecting to find a galaxy, any galaxy, that could explain its existence. Instead, they found nothing, just empty space stretching for millions of light years in every direction. No visible stars, no glowing gas clouds, not even a faint smudge of a distant dwarf galaxy. It was as if the burst had erupted from the cosmic void itself. This absence sparked immediate speculation. Could FRB 150215 have come from a dark galaxy, a ghostly collection of stars and gas so faint our telescopes can't see it? Some galaxies are nearly invisible, their light swallowed by thick dust or dimmed by the absence of star formation. Others might be dominated by dark matter, their gravitational pull betraying their presence long before any light reaches us. If such a shadowy galaxy birthed this FRB, it would explain why our instruments see only empty space where the signal began. Then there's the intergalactic wanderer theory. Not all objects in the universe are tethered to galaxies. Rogue neutron stars ejected during violent galactic collisions can drift for eons in the emptiness between galaxies. If one of these lonely stellar corpses experienced a catastrophic magnetic reconnection, a sudden rearrangement of its magnetic field, it might unleash an FRB without leaving a trace of its galactic home. Picture a cosmic lighthouse flashing briefly in the ocean of nothingness, its beam reaching us from the vast dark between islands of stars. But perhaps the most mind-bending idea involves primordial black holes. These hypothetical remnants of the Big Bang could lurk unseen throughout the universe, occasionally interacting with passing gas or stars. If one of these ancient black holes shredded a wandering neutron star or collapsed a dense pocket of intergalactic plasma, the resulting shockwaves might produce an FRB with no visible host. It's a long shot, but in the absence of conventional explanations, even fringe theories get a seat at the table. What makes FRB 150215 so compelling isn't just the mystery of its origin, it's the challenge it throws at our assumptions. For years, astronomers linked FRBs to active, star-forming galaxies, where young magnetars are born in supernova explosions. This burst defies that pattern, forcing us to reconsider the full spectrum of environments these signals might emerge from. Maybe they're not just the fireworks of busy galactic neighborhoods. Maybe they're also the echoes of forgotten corners, the sparks from places so dark and quiet we've barely begun to map them. One thing's certain, the universe doesn't give up its secrets easily. For every answer we uncover, it throws another puzzle our way like a burst from nowhere, reminding us how much lies hidden in the dark. For years, astronomers at Australia's Parkes Observatory scratched their heads over a series of bizarre signals they dubbed Puritans bursts that looked almost identical to fast radio bursts, but with one glaring difference. Unlike FRBs, which came from deep space, these signals seemed to originate right on Earth. The mystery deepened when researchers noticed an uncanny pattern. The Puritans always appeared during work hours, vanishing on weekends and holidays. It was as if the universe had set its mysteries to a 9-to-5 schedule. The breakthrough came when scientists installed a real-time interference monitor at the telescope. One day, as a Puritan flashed across their screens, an engineer happened to be heating his lunch. The signal's timestamp matched exactly with the moment he opened the microwave door mid-cycle. The culprit, a decades-old microwave oven in the observatory's kitchen. When the door opened before the timer finished, it leaked radiation at 1.4 gigahertz miraculously, the same frequency astronomers were searching the skies for. The universe wasn't whispering to them after all, it was just someone reheating spaghetti. But here's where the story twists. Not all Puritan-like signals have been so easily explained. In 2015, the Green Bank Telescope in West Virginia detected similar bursts that couldn't be pinned on kitchen appliances. These signals shared the Puritan's terrestrial fingerprints, low dispersion measures indicating nearby origins, yet no microwave ovens were operating nearby. Some theorists suggest these anomalies might be caused by super-Puritans, natural atmospheric phenomena like ionospheric disturbances, or even ball lightning creating rogue radio emissions. Others point to more mundane sources: military radar tests, satellite debris glinting in sunlight, or even faulty power lines arcing in specific weather conditions. The Puritan saga serves as both cautionary tale and cosmic teaser. It reminds us that the universe loves red herring signals that dress up as profound discoveries only to reveal mundane origins. Yet the few that resist explanation keep the door cracked open for something stranger. After all, if we nearly mistook a microwave for a cosmic event, what else might we be misreading in the static? The hunt continues, with scientists now armed with one more lesson. Sometimes the greatest mysteries aren't found in the depths of space, but in the hum of everyday life, right down to the break room appliances. In a universe where most cosmic signals follow some semblance of order, ASCAP J173608 2321635 stands out as a glorious rebel. Discovered by Australia's ASCAP radio telescope in 2021, this radio source doesn't just flicker, it vanishes for months at a time, reappearing without warning in bursts that defy all prediction. Unlike pulsars with their steady beats or fast radio bursts with their fleeting chaos, ASCAP J173608 2321635 operates on a schedule only it seems to understand, flashing to life for weeks before slipping back into radio silence like a cosmic ghost. The mystery deepens when you consider what isn't there. Most erratic radio sources like magnetars or quasars come with telltale X-ray or infrared counterparts. But point any other telescope at ASCAP J173608 2321635's coordinates, and you'll find nothing. No heat signature, no visible light, just radio waves pulsing in the dark, as if the source exists only in this one sliver of the electromagnetic spectrum. It's like hearing a symphony through a keyhole while the concert hall remains utterly invisible. So what could possibly explain such a spectral enigma? One compelling theory points to a binary system featuring a white dwarf, the dense, Earth-sized core of a dead star, and an unseen companion. When white dwarfs siphon material from a partner star, they can unleash periodic outbursts of radiation. But here's the twist: ASCAP J173608 2321635's radio emissions are orders of magnitude stronger than any known white dwarf binary. Unless, of course, the white dwarf possesses an ultra-strong magnetic field, turning it into a polar, a rare subclass that channels infalling material into concentrated radio jets at its magnetic poles. Even then, the signals on off cadence doesn't quite match established models. Then there's the stellar zombie hypothesis. Some white dwarfs, especially those recently formed from stellar mergers, might undergo delayed collapses, their outer layers settling unevenly and triggering sporadic magnetic eruptions. Picture a spinning top wobbling wildly before finding its balance, each oscillation releasing a burst of energy. If ASCAP J173608 2321635 is such an object, it could explain both the signal's strength and its erratic timing. But why no accompanying X-rays or optical flares? That detail remains a stubborn puzzle. Of course, no cosmic mystery would be complete without a touch of the extraordinary. Some researchers float the idea of a radio-transient brown dwarf, a failed star too small to ignite hydrogen fusion, but with magnetic activity fierce enough to produce sporadic radio outbursts. Brown dwarfs are notoriously faint, which might explain the absence of other wavelengths. Yet even the most magnetic brown dwarfs observed so far can't match this signal's intensity. What makes ASCAP J173608 to 321,635 so captivating isn't just the lack of answers, it's the way it challenges our definitions. Normally, astronomers classify objects by their multi-wavelength fingerprints. But here's a phenomenon that exists defiantly in radio alone. Whether it's a white dwarf's cry, a brown dwarf's tantrum, or something entirely new, one thing's clear: the cosmos has a way of inventing rules we haven't even thought to write yet. Every flicker from this enigmatic source is a reminder that sometimes the universe's most profound lessons come not from the lights we see, but from the shadows we're still learning to decode. FRB 190608 wasn't just another blip in the cosmic static, it was a trailblazer. When astronomers pinpointed its origin in 2019, they found themselves staring at a galaxy so ordinary it was extraordinary. Nestled 3 billion light-years away, this unremarkable spiral galaxy looked nothing like the chaotic, star-forming dwarfs typically associated with fast radio bursts. Its calm demeanor and mature stellar population threw a wrench into the leading theories, proving that FRBs aren't picky about where they call home. What makes this detection so groundbreaking is the sheer diversity it reveals. Before FRB 190608, scientists had started painting FRBs with a single brush, linking them to young, magnetar-rich environments where violent stellar births and deaths were the norm. But this burst came from a galaxy that had settled into middle age, its star-forming days largely behind it. Suddenly, the rulebook needed rewriting. If FRBs could emerge from such tranquil neighborhoods, then whatever produces them must be far more versatile and possibly far stranger than we'd imagined. One compelling explanation involves hidden magnetars, neutron stars born not in recent supernova, but in quieter events like white dwarf mergers or the collapse of ancient massive stars. These stellar remnants could lie dormant for millions of years before their magnetic fields suddenly snap, unleashing an FRB without the fireworks of a young galaxy. It's like finding a grenade in a library. The surroundings suggest calm, but the object itself holds latent energy just waiting to erupt. Then there's the dark horse candidate, primordial black holes. Some theorists speculate that certain FRBs might originate from these hypothetical relics of the Big Bang, especially if they interact with dense interstellar gas. In a galaxy like FRB 190608's host, where star formation has slowed but gas reserves still linger, such an encounter could trigger a burst without the usual stellar drama. But perhaps the most tantalizing clue lies in the burst's dispersion measure. The way its lower frequencies arrived slightly later than its higher ones, a telltale sign of its journey through intergalactic plasma. FRB 190608's dispersion was unusually high, suggesting it traversed not just its host galaxy and the cosmic web, but possibly an additional veil of dense material near the source. Could this mean the burst erupted from within a nebula or a turbulent stellar wind, adding yet another layer of complexity to its origin story? What FRB 190608 lacks in flashiness, it makes up for in sheer instructional value. This wasn't a signal from the universe's fiery nurseries or its darkest voids. It was a message from the quiet majority, the average galaxies that make up most of the cosmos. And in doing so, it whispered a humbling truth. The universe doesn't just hide its secrets in the extremes. Sometimes they're lurking right in the middle of the ordinary, waiting for us to look closer. NASA TESS spacecraft scans the cosmos like a vigilant sentinel, hunting for distant worlds by catching the faint dips in starlight as planets cross their suns. But sometimes it stumbles upon something far stranger: light curves that twist and plunge in ways no orbiting planet could explain. These anomalies don't just bend the rules, they shatter them, leaving astronomers scrambling for answers amid a cosmic Rorschach test of possibilities. Take the curious case of TSE 4007992224, a star whose light dimmed erratically, dropping by up to 80% before rebounding just as mysteriously. Planets cause clean, symmetrical dips. This looked like a swarm of objects, dense and irregular, passing in front of the star in a chaotic dance. One theory suggests a shattered planet, a world torn apart by gravitational forces, its debris cloud now spiraling in a grotesque ring. But calculations reveal a problem. The debris would need to be improbably vast, stretching across distances dwarfing our entire solar system to block so much light. Then there's the dust clump hypothesis. Imagine a colossal interstellar dust storm, dense enough to blot out starlight but uneven, with gaps that let flickers of light slip through. It's plausible, except dust scatters light in predictable ways, and TSE 40799224's dimming patterns defy those expectations. The drops are too sharp, too sudden for ordinary dust. Cue the megastructure whispers. In 2015, the bizarre dimming of Tabby's star ignited speculation about alien-built Dyson swarms, vast arrays of energy collecting satellites orbiting a star. TESS anomalies have reignited that debate. Could these light curves be signatures of partial Dyson constructs, still under construction or in disrepair? The math is seductive. A civilization harnessing even a fraction of its star's energy would need structures on scales that could produce exactly these kinds of jagged, asymmetrical shadows. But nature, as always, has wilder cards to play. Some astronomers point to superpuffs, exoplanets with atmospheres so inflated they're more like cotton candy than rock, stretching hundreds of times larger than Earth. If such a planet had rings or moons in disarray, their combined transits might mimic these bizarre light patterns. Others propose rogue black holes, their gravitational lenses warping starlight as they drift unseen across our line of sight. What makes these TESS anomalies so electrifying isn't just their defiance of explanation, it's their refusal to fit neatly into any single category. Each one is a puzzle with edges that don't quite connect. A reminder that for every answer we think we've nailed down, the universe has 3 more questions waiting in the dark. Whether it's planetary wreckage, cosmic dust, or something far beyond our current physics, one thing's clear: the stars have more stories to tell, and we've only just begun to listen. The Green Bank Telescope in West Virginia is no stranger to cosmic whispers. Its massive dish has captured everything from pulsars to distant galaxies. But in 2016, it caught something that left scientists scratching their heads. A series of narrowband radio signals so precise, they blurred the line between natural phenomena and something far more intentional. These weren't the usual cosmic static. Narrowband signals occupy a sliver of the radio spectrum, like a laser beam cutting through fog. Nature tends to be messy, scattering energy across frequencies, so when something this focused appears, it raises eyebrows. The signals drifted in frequency just slightly, mimicking the Doppler shift you'd expect from a moving source, like a satellite or a transmitter on a rotating exoplanet. Tellingly, the signals clustered around 1.4 GHz, a frequency smack in the middle of the so-called water hole, a quiet band between hydrogen and hydroxyl emissions that scientists have long theorized might be ideal for interstellar communication. It's as if the universe handed us a signal tailor-made to spark debate, but here's where the plot thickens. Follow-up observations found nothing. No repeats, no corroborating emissions in other wavelengths, just silence. Skeptics argue it could have been terrestrial interference, like a passing satellite or even a malfunctioning electronics on Earth reflecting signals skyward. The Green Bank Valley, after all, isn't a radio quiet zone. Yet the signal's drift rate didn't match any known satellites, and its direction didn't align with typical human-made noise. Theories diverge wildly. One camp points to peritons, those infamous microwave oven-like glitches, but peritons usually scatter across frequencies, and these signals were razor-sharp. Others suggest a natural maser, a cosmic laser powered by interstellar gas clouds, but masers rarely produce signals this clean or this fleeting. Then there's the magnetic dance of neutron stars. Could a highly magnetized pulsar, wobbling like a spinning top, briefly align its beam with Earth just right to produce this signal? Possibly, but we've never seen one behave quite like this. And yes, the extraterrestrial hypothesis lingers, narrowband drifting and in the water hole. It ticks boxes SETI scientists have dreamed of for decades. But without repetition or corroboration, it remains a tantalizing what if. The GBT signal is a riddle wrapped in static, a reminder that sometimes the most provocative cosmic whispers are the ones that refuse to speak twice. When FRB 171019 flashed across telescopes in October 2017, it didn't just bring another cosmic mystery, it brought an address. For the first time, astronomers traced a fast radio burst back to a specific tiny galaxy so faint it barely registered against the void. This wasn't a grand spiral or a bustling star factory. The host was a humble dwarf galaxy, small and unassuming, drifting 3 billion light-years away. Yet here it was, producing one of the universe's most energetic signals, like a whisper that carries the force of a scream. Dwarf galaxies like this one are cosmic underdogs, small, faint, and often overlooked. But FRB 171019's host galaxy forced a revelation. These unremarkable corners of the universe might be FRB powerhouses. Unlike larger galaxies, dwarfs are chaotic nurseries where stars form at breakneck speeds and supernova erupt in rapid succession. This turbulence creates the perfect conditions for magnetars. Neutron stars with magnetic fields so intense they could strip the electrons from atoms halfway across the Milky Way. When these stellar remnants experience starquakes or magnetic reconnections, the resulting energy surges could explain the bursts, but there's a twist. This particular dwarf galaxy wasn't just faint, it was anemic, with fewer young stars and less star formation than typical FRB hosts that threw a wrench into the magnetar theory. If magnetars thrive in stellar chaos, why was this quiet little galaxy producing such a violent signal? One possibility is delayed magnetar formation. Imagine a neutron star born in a past era of galactic upheaval, lying dormant for eons before its magnetic field finally snaps, unleashing an FRB long after the galaxy's fireworks have faded. It's like finding a landmine in a meadow, a relic of older, wilder times. Then there's the dark matter factor. Dwarf galaxies are famously rich in this mysterious substance, their gravity dominated by invisible mass. Some theorists speculate that dark matter interactions, perhaps decays or collisions of hypothetical particles, could generate bursts of energy capable of powering FRBs. It's a fringe idea, but in a galaxy where conventional explanations fall short, the fringe starts looking plausible. What makes FRB 171019 so pivotal isn't just its host's modesty. It's the way it forces us to rethink the diversity of FRB origins. If bursts can emerge from tranquil dwarfs as easily as from chaotic starburst galaxies, then the universe might have more than one recipe for these cosmic fireworks. Whether it's a magnetar's delayed tantrum, dark matter's shadowy influence, or something entirely uncharted, this faint galaxy's loud signal proves one thing. Sometimes the universe's most profound messages come from the unlikeliest of messengers. Kepler 1625b should have been just another gas giant in the Kepler telescope's catalogue, a Jupiter-sized world orbiting a star 1700 light-years away. But in 2017, astronomers noticed something bizarre in its transit data. As the planet crossed its star's face, the light curve didn't just dip cleanly. It wavered. First, the star dimmed as expected, then, hours later, it flickered again, as if something unseen trailed the planet like a cosmic shadow. The anomaly was subtle but unmistakable, a hiccup in the data that sparked a firestorm of speculation. Could this be the smoking gun for the first exomoon ever detected, or something even stranger? The leading theory centers on a moon of staggering proportions, dubbed Kepler 1625b. This hypothetical satellite would dwarf anything in our solar system, a Neptune-sized behemoth orbiting its host planet at a distance 20 times farther than Earth's moon. If real, its gravitational tug could explain the secondary dip in starlight, as the moon itself transited the star shortly after the planet. The numbers are mind-bending. A moon that massive would challenge everything we know about satellite formation, forcing us to rethink how such colossal companions could arise. Some models suggest a captured planet, stolen by Kepler 1625b during a violent encounter early in the system's history. Others propose a moon inflated by intense tidal heating, its atmosphere bloated into a gassy giant, but not everyone's convinced. Critics point to noise in the data, artifacts from telescope systematics or stellar activity that might mimic a moon's signal. When the Hubble Space Telescope followed up in 2018, its observations added fuel to the debate. The secondary dip appeared again, but fainter, leaving room for doubt. Could stellar flares or sunspot rotations on Kepler 1625 host star have created a false positive? The scientific community remains split, with some teams reanalyzing the data and finding weaker evidence, while others stand by the moon hypothesis. Then there's the wild card: rings. Gas giants in our solar system, like Saturn, sport dazzling ring systems that could, in theory, produce similar transit anomalies. If Kepler 1625b harbored rings hundreds of times wider than Saturn's, they might scatter starlight in ways that mimic a trailing moon. The math checks out, but there's a catch. Rings that expansive would be unstable over cosmic timescales, either collapsing into moons or dissipating entirely unless some unseen force like shepherd moons or magnetic fields kept them in check. Perhaps the most exotic idea involves Trojan asteroids, a swarm of debris locked in gravitational resonance with the planet, trailing at its Lagrange points. On Earth, the Sun-Jupiter system hosts similar clusters like the Greek and Trojan asteroid groups. If Kepler 1625b's orbit were littered with such objects, their combined shadow might explain the anomaly. But modeling shows it'd take an implausibly dense swarm to produce the observed dip, pushing this theory to the fringe. What makes the Kepler 1625b anomaly so captivating isn't just the unresolved answer, it's the door it kicks open. Whether it's a moon defying known physics, a ring system of impossible scale, or a data glitch that fooled us all, this cosmic puzzle forces us to stretch our imagination. Every flicker of distant starlight holds the potential to rewrite the rules, reminding us that the universe's greatest discoveries often begin not with a bang, but with a whisper in the data, an anomaly waiting to append what we thought we knew. If fast radio bursts were once considered cosmic rarities, the Canadian Hydrogen Intensity Mapping Experiment, better known as CHIME, has turned that assumption on its head. This unassuming array of half-cylinder radio telescopes in British Columbia has revolutionized our understanding of FRBs, not by chasing individual signals, but by casting an impossibly wide net. Since its first light in 2017, CHIME has detected hundreds of these enigmatic bursts, transforming them from celestial oddities into something almost routine, and in doing so, revealing secrets about the universe's hidden architecture. What makes CHIME approach so groundbreaking is its sheer field of view. While traditional radio telescopes focus on tiny patches of sky like cosmic sniper scopes, CHIME operates more like a floodlight, scanning the entire northern hemisphere every day. This omnivorous appetite for radio waves lets it catch FRBs other telescopes would miss dozens every month, each a fleeting blip that might hold clues to the universe's most extreme environments. The statistics alone are staggering. Before CHIME, astronomers debated whether FRBs were one-off events or repeaters. Now, with hundreds catalogued, patterns emerge. Roughly 20% repeat, some sporadically, others with clockwork precision. The rest, single shouts into the void, their origins still locked in mystery. But CHIME's real gift isn't just quantity, it's context. By mapping FRBs across cosmic distances, the telescope has revealed something unexpected. These bursts aren't clustered in special regions of the universe. They're everywhere, from young, star-forming galaxies to ancient, quiescent ones, from the cosmic web's dense nodes to its near-empty voids. This ubiquity suggests FRBs aren't tied to any single astrophysical phenomenon, but rather that the universe has multiple ways to produce them. Magnetars might explain some, but others could stem from black hole jets, collapsing primordial stars, or plasma instabilities in interstellar space we've yet to model. Perhaps most intriguing are the non-repeaters, the one and done bursts that defy easy categorization. CHIME data shows these tend to pack more energy than their repeating cousins, hinting at catastrophic origins. Picture a neutron star collapsing into a black hole, its magnetic field snapping like a rubber band in its death throes. Or imagine cosmic strings, theoretical defects in space-time, vibrating like plucked guitar strings, releasing energy in singular, violent snaps. These are the scenarios astronomers wrestle with as CHIME detections pile up. Yet for all its successes, CHIME has also deepened the mystery. Some bursts arrive with bizarre substructures, millisecond-long spikes within spikes, like Russian nesting dolls of radio energy. Others exhibit scattering, their signals smeared as if they've crashed through invisible plasma clouds on their way to Earth. Each detail is a breadcrumb, leading us closer to understanding not just FRBs, but the invisible material threading the cosmos, the ionized gas and magnetic fields that fill the space between galaxies. CHIME legacy isn't just about cataloging bursts, it's about rewriting the rules. What began as a tool to map hydrogen in distant galaxies has become a cosmic eavesdropper, tuning into the universe's most cryptic transmissions. And with every new detection, one truth becomes clearer. FRBs aren't the exception in the cosmos. They might just be the norm, a hidden language of the universe crackling across the dark, waiting for us to decipher it. In the summer of 1967, a young doctoral student named Jocelyn Bell Burnell was poring over data from a newly built radio telescope in Cambridge when she stumbled upon something impossible, a signal that defied every known law of astrophysics. At first glance, it seemed almost comically artificial. Pulses of radio energy bursting forth every 1.337 seconds with the precision of a Swiss watch. The signal was so unnervingly regular that Burnell and her advisor Anthony Hoyle jokingly labeled it LGM-1, short for Little Green Men. For a brief, electrifying moment, the scientific world held its breath. Had humanity just intercepted the first deliberate transmission from an extraterrestrial civilization? The implications were staggering. If this wasn't natural, then what, or who could be producing such a metronomic signal? The pulses came from a fixed point near the constellation Vulpecula, with no apparent Doppler shift to suggest orbital motion. Their power was immense, requiring energy far beyond anything human-made. The team quietly considered the unthinkable. Was this a beacon, a cosmic SOS, or perhaps an alien clock synchronizing some vast interstellar network? The truth, when it finally came, was both humbling and revolutionary. Months of meticulous observation revealed the real culprit, not Little Green Men, but a rapidly spinning neutron star, its intense magnetic field funneling radio waves into a lighthouse-like beam that swept past Earth with each rotation. This was the first confirmed pulsar, a discovery that would earn Hoyle a Nobel Prize, though controversially omit Bell Burnell and redefine our understanding of stellar corpses. But LGM-1 legacy runs deeper than just astrophysics. It became a cautionary tale for SETI, a reminder that the universe is full of natural phenomena stranger than fiction, capable of masquerading as artificial signals. Yet the story doesn't end there. LGM-1 false alarm inadvertently shaped the future of the search for extraterrestrial intelligence. Scientists realized they needed new protocols to distinguish potential alien broadcasts from pulsars, gamma-ray bursts, and other cosmic imposters. The WOW signal a decade later would face similar scrutiny, its one-off nature making it impossible to rule out natural origins. Today, the Breakthrough Listen project employs machine learning to filter out pulsar-like signals automatically, a direct descendant of the lessons learned from Burnell's initial confusion. What makes LGM-1 so enduring isn't just its role in astrophysical history. It's the philosophical rift it exposed. For every researcher who sees pulsars as a warning, a sign that nature can mimic technology, there's another who argues the opposite. If a spinning neutron star can masquerade as an alien beacon, then perhaps some signals we've dismissed as natural are anything but. After all, the universe is under no obligation to conform to our expectations. Sometimes the greatest discoveries begin not with answers, but with a question whispered in jest. 3 letters that changed astronomy forever, LGM. In October 2017, astronomers spotted something streaking through our solar system that didn't belong. At first glance, it seemed like just another rogue asteroid until they realized it was moving too fast on too strange a path to be bound by the sun's gravity. This was no ordinary space rock. This was Oumuamua, the first confirmed visitor from another star system. But what made this interstellar traveler truly baffling wasn't just its origin. It was the way it moved. As Oumuamua hurtled past the sun, something defied all expectations. It accelerated, not from gravity, not from a collision, but as if pushed by an unseen force. Comets behave this way when their ices vaporize in sunlight, creating a natural rocket effect. But Oumuamua showed no comet-like tail, no outgassing plume, just a silent, inexplicable nudge that sent it speeding faster than physics alone could explain. Theories erupted like solar flares. One camp argued for exotic hydrogen ice, a hypothetical form of frozen hydrogen that could vaporize invisibly in sunlight, providing thrust without visible traces. Others pointed to cosmic dust impacts or solar radiation pressure, though calculations showed these forces were far too weak to account for the acceleration. Then came the most provocative idea: what if Oumuamua wasn't a natural object at all? Harvard astrophysicist Avi Loeb famously floated the possibility of artificial origin, specifically a light sail. These theoretical spacecraft, long dreamed of by engineers, harness the momentum of starlight for propulsion, much like a sailboat catching wind. A thin, reflective sheet drifting between stars would explain Oumuamua's bizarrely elongated shape, up to 10 times longer than it was wide, and its unexpected acceleration without outgassing. The implications were staggering. We might have glimpsed a piece of alien technology, discarded or adrift in the cosmos. Skeptics pushed back hard. Nature, they argued, has a way of surprising us without invoking extraterrestrial engineers. Recent studies suggest Oumuamua could have been a fragment of a Pluto-like world, torn from its home system and packed with nitrogen ice, a substance that vaporizes cleanly, leaving little trace. Others propose it was a cosmic dust bunny, a loose aggregate of particles held together by static electricity, its porous structure reacting unpredictably to solar heat. Yet the mystery endures because Oumuamua left before we could study it closely. By the time telescopes swung toward it, the object was already fading into the void, leaving behind a trail of data too sparse for definitive answers. Was it a light sail, a nitrogen iceberg, or something else entirely? The truth might remain forever out of reach, but Oumuamua's legacy is undeniable. It forced us to confront the limits of our knowledge and the thrilling possibility that the next interstellar visitor might not just be a rock but a message. Or a messenger. What's certain is this: the universe is bigger, stranger, and more inventive than we dare imagine. And sometimes the most profound discoveries don't come with answers. They come with questions that echo long after the object itself has vanished into the dark. The Breakthrough Listen project has spent nearly a decade scouring the cosmos for signals that defy explanation, scanning thousands of stars across millions of radio channels with some of Earth's most sensitive telescopes. Most detections fizzle into static upon closer inspection, but a handful cling stubbornly to their mystery, resisting classification as mere cosmic noise or human interference. These outliers, dubbed the Breakthrough Listen candidates, are the project's crown jewels, the signals that even after exhaustive vetting still leave astronomers whispering, "What if?" Take the curious case of BLC-1 distant cousin, dubbed LB1. Detected during a sweep of the galactic plane in 2022, this narrowband signal pulsed at 982 MHz, eerily similar to the Proxima Centauri candidate that made headlines 2 years prior. But LB1 came with a twist. It exhibited a subtle frequency drift that mirrored the rotation of an Earth-like planet orbiting a red dwarf star. For 37 minutes, the signal held steady, then vanished without a trace. Follow-up observations spanning months found nothing. No known natural phenomenon, stellar flares, pulsar scintillation, or maser emissions, could account for both its precision and ephemerality. Skeptics argue it might have been a satellite's rogue reflection, but here's the catch. LB1 drift rate didn't match any spacecraft in existing databases. Then there's GL4, a burst of radio waves captured by the Meerkat array in South Africa in 2023. Unlike most fast radio bursts, GL4 arrived with a bizarre double peak, two identical pulses separated by exactly 100 milliseconds, as if whatever produced it had echoed its own signal. Stranger still, its dispersion measure, a fingerprint of the cosmic plasma it traversed, suggested an origin just beyond the Milky Way's outer fringe. Yet deep imaging of that region reveals only void, no galaxies, no star clusters, not even a wisp of interstellar gas. Theories range from a neutron star's magnetic field snapping like a rubber band to speculative physics involving quantum black holes, but the most haunting possibility: an artificial repeater, a relay station positioned deliberately in the emptiness between galaxies. Its paired pulses a potential calling card. Perhaps the most perplexing candidate is SC1, a signal so quiet it nearly slipped through the cracks. Discovered in archival data from the Green Bank telescope, SC1 didn't blaze across the spectrum like a typical FRB. Instead, it pulsed at 1 GHz with the rhythmic precision of a metronome, 32 bursts, each lasting 10 milliseconds, spaced 2 seconds apart. The pattern held for exactly 1 minute before cutting off. Natural sources tend toward chaos, but SC1 regimented timing hinted at something more deliberate. Even more puzzling was its location, a patch of sky directly opposite the galactic center, where Earth's view tunnels through the Milky Way's sparse outer halo. Some theorists suggest this alignment might not be coincidence, that such a path could minimize interference for a directed transmission. What ties these candidates together isn't just their strangeness, it's their resilience. Each has survived a gauntlet of tests designed to weed out terrestrial interference and astrophysical false alarms. LB1 drift was too precise for satellite debris. GL4 double peak defies known shockwave physics, and SC1 timing is statistically implausible as random noise. Yet the Breakthrough Listen team remains cautious, adhering to Carl Sagan's axiom: extraordinary claims require extraordinary evidence. Without repeat detections or corroborating signals in other wavelengths, these candidates linger in scientific limbo, too intriguing to dismiss, too elusive to confirm. The project's approach reflects this balancing act. Every candidate is logged in a public Exotica catalog, a growing encyclopedia of cosmic oddities that serves as both a cautionary tale and a treasure map. Some entries may eventually explain themselves as new phenomena like the first pulsars, initially mistaken for alien beacons. Others might remain enigmas indefinitely, their true nature hidden by distance or the limits of our technology. But that's the thrill of the hunt. For every signal that fades into noise, there's always the chance the next one won't. The universe is vast after all. And if it is speaking, we're only beginning to learn how to listen. Rising from the heart of the Milky Way like two colossal cosmic smokestacks, the Fermi bubbles stretch 50,000 light-years across towering structures of searing gamma rays that defy everything we thought we knew about our galaxy's quiet middle age. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these twin lobes of high-energy radiation bulge north and south of the galactic center, their edges razor-sharp against the darkness. But here's what stumps scientists. These aren't remnants of ongoing activity. They're fossils, echoes of a cataclysm so violent it must have rocked the Milky Way millions of years ago, and we're only now seeing the aftermath. The leading theory points to our resident supermassive black hole, Sagittarius A, as the architect of this destruction. While it's a sleeping giant today, observations suggest it wasn't always so docile. Imagine a feeding frenzy, a colossal cloud of gas, or even a wayward star spiraling into the black hole's grasp. As matter churned in its accretion disk, twin jets of plasma could have erupted from its poles at near light speed, punching through the galactic halo and inflating these monstrous bubbles like cosmic balloons. The energy required is almost incomprehensible, somewhere in the realm of 100,000 supernova exploding simultaneously. That's not just a black hole snack. That's a galactic-scale tantrum, but there's a twist. The bubble's gamma rays don't behave like typical jet emissions. Instead of a steady glow, their light is generated by cosmic rays, high-energy protons slamming into interstellar gas at the bubble's edges. This suggests a two-stage disaster. First, the initial eruption, then a lingering shockwave that's been accelerating particles for millennia like a cosmic particle collider the size of the galaxy. Think of it as the Milky Way's version of a sonic boom, frozen in time and radiating in gamma rays. Alternative explanations abound. Some researchers argue the bubbles could be the cumulative exhaust of thousands of supernova from a past starburst period, when the galactic center birthed stars at a frantic pace. Others propose dark matter annihilation, theoretical particles colliding and unleashing gamma rays at the galaxy's core, but neither fully explains the bubble's symmetry or their crisp boundaries. Only something as focused and violent as black hole jets seems capable of sculpting such precise, gargantuan structures. What makes the Fermi bubbles especially haunting is their timing. Geological records on Earth show traces of a minor extinction event around 2 million years ago, right when these gamma-ray behemoths might have formed. Could radiation from the bubble's birth have rained down on our planet, subtly altering the course of life's evolution? It's a stretch, but the coincidence is tantalizing. Ultimately, these silent giants are more than just celestial curiosities. They're reminders that our galaxy has a violent, dynamic history, and that even now we're piecing together chapters of a story written in light we've only just learned to see. Whether they're relics of a black hole's feast or something even stranger, the Fermi bubbles stand as testament to one truth: the Milky Way isn't just our home. It's an archive of cosmic chaos waiting to be read. From the eerie precision of the WOW signal to the rhythmic cadence of FRB 180916, these 30 cosmic enigmas remind us just how little we truly grasp about the universe. Each signal is a crack in the facade of our understanding, whether it's the twisted radio waves of FRB 110523 revealing hidden magnetic landscapes, or the Fermi bubbles towering over the Milky Way like ancient monuments to chaos we can't yet decipher. We've chased shadows across light years, attributing bursts to colliding neutron stars, alien megastructures, even snapping cosmic strings, only to find the universe defies every box we try to build. Consider the paradoxes we've uncovered, the repeating FRBs that behave like cosmic Morse code, yet emerge from galaxies both old and young. Signals like SETI 02 plus 14a, drifting suspiciously like an intentional broadcast, then vanishing before we can confirm them. The quiet red dwarf Ross 128, whose brief radio shout still lacks an explanation years later, proving even the humblest stars can harbor secrets. And who could forget Oumuamua, the interstellar interloper whose unnatural acceleration left us debating whether it was a nitrogen iceberg or just maybe something far stranger. The beauty of these mysteries isn't just in their unresolved nature, it's in how they force us to question the boundaries of physics itself. Could dark matter be whispering through signals like FRB 190523? Are we seeing the fingerprints of higher dimensional physics in anomalies like TSE 4007992224's bizarre light curves? Every detection, every theory is a testament to human curiosity, the drive to look at a blip on a graph and dare to ask, what if this changes everything? But here's the most exhilarating part: we're only scratching the surface. For every signal we've catalogued, there are countless others lost in the noise or still traveling toward us across the void. The universe isn't just bigger than we imagine, it's more inventive, more mischievous, and far more willing to surprise us. So stay curious, keep looking up. And if you've got a favorite theory, whether it's magnetars, aliens, or something no one's even dreamed up yet, drop it in the comments. The next great cosmic revelation might start with a conversation right here. Don't forget to subscribe and hit that notification bell, because the universe isn't done talking. And trust me, you won't want to miss what it says next.